Hello once again. This is the third video in our series giving supplementary information for the lab portion of ENGR 467 Real-Time and Embedded System Design. I'm Logan and I'm quickly going to go over a few topics concerning today's lab, task scheduling and semaphores. As always, if you're looking for course information, refer to the syllabus on Canvas. Make sure you have successfully completed lab number 2 as we will be continuing on from where we left off. Today's video will be rather short, and we're going to start with a discussion of tasks. In embedded systems, tasks are small pieces of a program that operate continuously. The definition of a task is somewhat fluid, and often you'll hear the terms thread or process used interchangeably. Technically speaking, those terms are more specific, but it doesn't matter for this course. Each task has its own registers and stack memory, and is defined by a priority. More vital tasks, such as one dealing with deployment in an airbag system, will have a higher priority compared to others. A task can be in a number of states, including running, waiting, or ready. When in a running state, the task is actively performing its action. A ready state denotes the task needs to be run and is waiting on the operating system to allow it to do so. Similarly, when a task is in the waiting state, it is watching for a change in something, such as a keyboard. An operating system is used to allow multiple tasks to run concurrently. Although these tasks are never running at the same time, they appear to be running in parallel to the user. This is known as pseudo-parallelism. Tasks are scheduled by the scheduler, a part of the operating system. There are many different types of scheduling algorithms, and each one has both pros and cons. These algorithms can either be preemptive, meaning they allow tasks to be interrupted before completion, or non-preemptive. Common scheduling algorithms are first in, first out, round robin, and shortest job first. The second topic of discussion today is what's known as a semaphore. Semaphores are used to control access to shared resources to ensure a race condition does not arise. One way of thinking about a semaphore is to envision it as a key. A resource has a lock and only the process with the key is able to access it. Once that process is done, they make sure to lock up the resource and return the key. In actuality, a semaphore is an integer variable, typically initialized to 1. When a process wants to access the resource, it performs a wait operation. This checks to see if the semaphore is positive. If it is not, the process must wait until it is. Once this happens, the process can acquire the semaphore, or key, and decrement the value. Once done, the process then uses the signal operation, incrementing the semaphore and notifying any waiting processes. This can be seen here. Process pi issues a wait operation to acquire the semaphore, runs its critical section, and then releases it. This is the most basic setup you will see to access a semaphore. Using mutual exclusion has some consequences, however. Although we can usually eliminate most race conditions, semaphores also introduce a number of other considerations, such as deadlock, priority inversion, and starvation. Deadlock is a condition where two different processes are waiting to acquire a semaphore, but can only do so once the other has released it. Because neither can release their respective semaphore, the program cannot progress. Priority inversion will be discussed in the future, but essentially, a lower priority task is given precedence over one with higher priority. Lastly, starvation is a condition where there is execution but no progress. For example, there may exist a situation where two processes switch back and forth but do not allow a third process to run. The first two processes depend on the third, but it is never executed. Deadlock and priority inversion are serious issues and have likely been the cause of a number of serious malfunction in industries such as aviation and aerospace. One such example was the Mars Pathfinder spacecraft. Built using the VxWorks RTOS, which allows preemptive priority scheduling, a low priority process acquired a semaphore that was required by a very high priority bus management task. Because this task could not acquire the semaphore, the system was forced to reset, leading to interruptions in communication and performance. Engineers managed to detect the problem on Earth and solved it by switching to a different scheduling method. Once again, it's now your turn to complete the lab procedure. The lab is relatively short and follows a similar method to the two previous labs. We've done well blinking an LED, and today is no exception. In part 1, we'll be using a task in Semaphore to toggle the LED state. The result of this is the same as the 2 previous labs, a blinking blue LED. Part 2, however, gets significantly more interesting. Instead of blinking 1 LED, we're going to be toggling 3. Done correctly, it may not appear as you would expect, seen here. The LEDs all turn on, but do not turn off immediately. Give thought to why this might be, and answer the question in the lab report. Lastly, in part 3, we will make a small change in the configuration of the semaphore with a significant change to the output of the LED, once again shown here. That's all for this video. Make sure to complete the lab report and submit both it and your main.c to Canvas before the deadline.